All right. Happy Wednesday, everybody. Is everybody staying dry? Semi-dry? Do you know where your umbrellas actually are? They're not commonly used, so it's always a scramble when it actually rains. So we are going to start today something called Shell Balances, where we are going to put our newly acquired knowledge of stress tensors to use. So, just a quick review. If I had a parallel plates case, and I'm gonna put, whoops, and I'm gonna hopefully put I have okay. I have a non-reacting pen today. Pen. Okay. Why is it? Oh, this is a new one. Huh. I didn't. Okay, so now it's ready. Okay. Well then. It needed a moment to. So if I had a parallel plates case, now it doesn't wanna. And I need to erase. Oh well. I have parallel plates case, and I have x direction here and y direction here. And my only velocity, if I'm moving the lower plate vx, my only velocities are in x direction. In that case, we say, velocity is just vx, which depends on y, and a 0 in the other case, in the other direction. So nothing is really going microscopically in cross direction. So what was my shear stress, tau yx, in this case? That is one equation for parallel plates if I wake you up in the middle of the night. Or possibly it's worse in the middle of the morning. You need to know. However, this is very specialized for this case of parallel plates. My only non-zero velocity is the Vx one. So that momentum is the only one that can transfer across which plane? X momentum is transferred across y plane, down yx. Now, what happens if I have a more general situation? This tau yx doesn't remain the same. The formula. Is this the formula that you're going to use in any other applications that have the Cartesian coordinate system? If I'm asking, the answer is no. But the question is, which formula are you going to use? What is the generalized version of this? There's the tensor formula, yes. So there is a tensor version of it, which is sort of a shorthand notation. But I still need to, if I ask you, give me tau ix from that tensor notation. This is the tensor notation. Remember? The formula is primary on Monday. Nobody remembers it. There's a reason I played a divergence video. Because I want to determine what this term here is. Divergence of a vector field technically measures how much of it at every point I have a source or a sink of flow in this case. But that vector field could be anything else. So what are all of the terms here? What is gradient of V for a vector field? If I have, let's stay in 2D. If I have V that has two components, what is gradient of V? Matrix. That multivariate calculus, wasn't that your favorite class? Yes? No? Maybe? So what is gradient? No? No. X. So what do I do? So normally if I have gradient applied to scalar functions, typically, so if I had gradient of pressure, it would be derivatives of pressure in all the coordinate directions. However, here now I have a vector field. So I have components, Vx and Ui. So technically I have a gradient of each of those components. So I stack them up into a matrix. And that is essentially what your coding is. What it measures locally, just like a single derivative. A single derivative, if I had a graph of a function, single derivative is a slope. If a function that depends on one variable, if I take a derivative, it's basically the slope of that graph. So locally, at a point, what I do with the derivative, I'm locally linearizing the function. Yes? I'm just making it as a little straight line instead of something curved. And then I move over and I have a different straight line. That's the nature of nonlinear functions. But it's locally at that very point, the derivative is just a linear, simple straight line approximation of my function. This does the same. It's just difficult to see in 2D or 3D. So basically, the way I'm describing linear functions that work on vectors and send a vector to another vector is with matrices. So when I take a matrix, multiply it with a vector, I get another vector. So it's a function that goes from a vector to a vector. In calculus, you said, oh, function goes from R2 to R2 or R3 to R3. Yes? So I'm just sending a vector to a vector. Well, if I'm colliding bodies, one body moves with one vector. After collision, I'm moving in another direction. I need a function that moves a vector to another vector, right? We need those all the time in multiple directions. So basically, what gradient locally does is Jacobian, however complicated this table is. This is evaluated at point xy. It's a bunch of numbers. And those numbers describe a linear transformation, the one that is described with a matrix of constant entries, that is locally linearized for this field. Field might be complicated, but we can locally linearize it, and that's what Jacobian does. Just like the river, it's the generalization of a slope. It's a complicated little table because I have multiple directions. So I need to take derivatives with respect to all of those directions of all of those components of my vector field. But ultimately, this is a local linearization of a field. Possibly complex vector field. Excellent. So this formula now, in a cryptic way, says take, this is a tensor, that's why I have these two little lines underneath, simply to say that's a tensor. I often been writing actually omit those, but in certain notations, like it's common to put these two lines simply to say this is a table of numbers. Minus mu. This is a matrix. This is just a transpose of the same matrix. And then plus, this is a constant. Just take it as a constant. 2/3 mu, and there's a negative viscosity here. Kappa. Assume we know these. And then divergence of V. So, what is this? These individual elements are delta ij. What did I say delta ij is? Identity matrix, really. So, elements of identity matrix are 1 only on diagonal. So this delta is going to be 1 only if this ij is very equal to each other, otherwise it's 0. So it's just a shorthand notation. So let's now try to write this down in this case. So I know that my transpose is, well, nothing changes on diagonal. And this is going to be, what did I do here? This is supposed to be x. So I'm just going to flip, when I'm transposing the matrix, I'm just flipping things across diagonal. dvx dy and dvy dx. So my general tensor tau says that I'm minus mu gradient v plus gradient v transpose plus some constant minus kappa, divergence of velocity, and delta. So that is, what is now my tau yx? It's minus mu. What is a yx element of gradient? Which of these numbers is yx? Right? So basically, I'm going to sum this plus this, okay, to get elements. That's the good news about these measures. So even if you flip who is x and who is y, you get. Okay? So basically, there will be, so in this matrix, so this is a matrix, okay, a tensor, and it has each element within. Okay? And if I'm looking for a yx element, I'm going to take yx element of this, yx element of this, which is the transpose of the same. And then here, do I have delta yx? What is delta yx? 0. So this is not going to show up in shear stresses. Okay? Only normal stresses. So all I'm going to have is dvx dy plus dvy dx. So this is the generalized form plus 0, yes.
How can you repeat that again? Going back to, it's only going to have normal stress.
So this is identity matrix. Does identity matrix have anything non-zero off diagonal? Let me change the color here. So this is 1001. So this is x, y, y. You can also think about it as 1122, whatever you want to call it. And off diagonals are zeros. So that's just going to cancel this term. For my yx. However, it's going to show up for my tau x6. There will be a 1 here. There will be a divergence here, which is a scalar. It's a number times a constant plus 2 of these because they repeat. So my tau x6 is minus mu times 2 dvx dx. What is divergence? It's dvx dx plus dvy dy for a two-dimensional field, and then times 1. This is my normal viscous stress tau x6. It's the transfer of x momentum across x plane. Are we grasping, semi-grasping these formulas? Again, there's a reason why we torture young engineering minds through multivariate calculus. This is where it's used. This is what it's made for. Are viscous stresses all of the stresses that I have? Is that the only thing that is stressing me out if I'm sitting in a flowing fluid? No. What else is there? There's always hydrostatic stuff that's stressing me out whether the fluid is flowing or not. And that we separate. So this is a mathematical decision to separate because we also in different situations, flowing versus no flowing, you can isolate and measure each one separately. And then there's one more thing that is very specific of the fact that we are often choosing a static coordinate system, a system or control volume that is still sitting still, because most often our measuring devices, our valves, are sitting in one place, and stuff is flowing through, right? So stuff is flowing through, so at every time when you're measuring that pressure, you're measuring a different fluid. New stuff is constantly moving in. So there is also convective momentum transfer. Momentum that is simply physically moved into my domain in that time. Some of it is I'm just stressed out from relative difference in the fluid velocities within, and some of it is simply movement. Now, what moves in at any time? Let's say that I just have a piece of paper, and I'm having a general velocity going through that paper like this. How do I quantify which portion of this velocity, which is the general vector, is actually going through splitting my vector into components here to a local coordinate system. There is a component that is orthogonal to the paper, and then two other, if I put a coordinate system here, there's one orthogonal, and two others are in that plane, correct? Is anything moving in this plane going through the paper? Going through? No. So the only thing that's going through is normal component. Whatever this vector is in some general direction, I find its normal component. How do we solve? I need this normal direction here. And I need to somehow project this vector onto that normal direction. How do we do that using calculus tools? How do I project a vector on a vector? Dot product is a projection. Yes? So that's simply a tool for me to evaluate how much is moving through. Now, if that vector, if this is actually aligned with the coordinate system, and this is my y-plane, its normal is what we call delta y or j, or however you want to call the coordinate vector, ey, in all of the various courses, right? That normal is the coordinate vector in y direction. And that projection is actually dy. Yeah? When I do a dot product of the coordinate vector y with any velocity v, I get its y component, dy, by definition. Yes? All right. So, basically, if I want to measure what comes through this plane that is simply flown in momentarily, the momentum that is flown in through y-plane is momentum rho v times vy, projected for the normal component to that. Yes? So that's why my momentum tensor has all of these components. This is my convective tensor. So this is the stuff, everything that comes in. Possibly a pressure, hydrostatic, plus my tau, which I just told you how to do, right? Plus rho vi vj, this is stuff that just momentarily moved in with a different packet of fluid. Yes? Oh my goodness, the looks I'm getting. Okay? So ultimately it's a formula, but I want you to physically understand that these are ij components of a matrix. Okay? And this is how I get them all. This is the hydrostatic one. These are the viscous stresses. This is transfer of J momentum across pi plane. And these are rho vi vj simply measures how much stuff just moves in the back of the fluid. Okay? Those are my combined stresses. I call first two molecular and the second one convective. It's just a choice to separate them all mathematically. Technically, if my coordinate system was moving with the fluid at the same velocity, I would be always catching up with the convective one. I wouldn't feel it, I wouldn't have it in that coordinate system. But that's a moving coordinate system, right? And sometimes our measurement devices are moving with the coordinate system, right? So I have to account for that. There's a difference between the two. But that's just for you as a mental note. I have a static coordinate system, choice that I have to account for. So this is the delta ij. So pressure will show up only in x, x, y, y, z, z components. The normal one, because stacks only normally there's no shift. Yes.
So, like, if we were the pressure problem, would we use the combined stress one? Like,
That's what you're about to do. Okay, but I wanted to review this because this, and it's going to take a moment, so we're going to keep reviewing. But this is putting your multivariate calculus to use. So normally tau x minus mu dvx dy, that's just parallel plates. In general, I gotta account for much more. Okay, and I have transfer of all of the possible momentum components x, y, and z across all of the possible plates x, y, and z. That's why I have an entire table. Okay. My viscous stresses, tau, are not the only stresses. That's just viscous stresses because of the local differences, relative differences in velocity. I also have hydrostatic, and I have stuff that moves in, convective. So this is my combined stress tensor. Okay? And that's the one we have to put in our equations. So let's stop talking and actually start doing it. So normally this is just a general problem solving. I'm going to make my hints to it, and then we're going to just do an example and then review the steps again. It's the following. All right. I have a problem, fluid flowing somewhere. That somewhere has a geometry. So first I have to pick a coordinate system that I'm going to solve. First question is it Cartesian, is it cylindrical, or is it spherical? It kind of makes sense if I'm doing tube, it's going to be cylindrical. If I'm in anywhere straight, it's going to be Cartesian. Great. And then I also orient it, and I want to orient it so it makes my life easy. So if my parallel plates are this way, well, then I'm not going to orient my coordinate system this way so that I have a full tensor there. Right? So I want to orient my system so that as many velocity components as possible are zero. Just like in parallel plates, that zero and Vy solved a lot of our problems. We had a very simple shear stress expression, right? I didn't need to go into tensors. So basically, then within that system, there's sort of like a thin fluid element which we call a shell, which is really a little box in the coordinate system. And then we balance, so that's our little control volume. Remember thermodynamics and control volumes? Well, this is our little control volume. And the reason why people often refer to this as microscopic transfer is because we're actually going to go to sort of like around the point, like a very small thing. And we're going to balance things across that control volume, and then shrink the control volume to a point. And then I'm going to get a differential equation. And then I'm going to solve. Sounds really easy. This part is that the best case is if you can figure out that differential equation to be ordinary differential equation. The most beautiful thing is when you have only one velocity component that is not zero, that depends on only one other coordinate vector, like Vx of y. The moment you have Vx of x and y, so in numerical, the analytical solution becomes trouble. So basically for most analytical approaches, this better be an ODE. We can often just pose the problem with a B. And solve it later, maybe with some software or something. Posing the problem we're doing this balance is the first important step. And that process, the key thing is the balance. Balance is always, well, rate of whatever it is that I'm balancing. Right now we're going to balance momentum, and I have just told you what the combined momentum is, right? That's the introduction to this. The rate of whatever you're balancing, now you're balancing momentum. Rate of momentum change is rate of momentum coming in minus rate of momentum coming out plus whatever, in this case, what can change momentum, whatever action of the external forces does to whatever you're balancing. Now, this case, or sometimes internal creation as well. So, in this case, what can change momentum is really a force acting on the fluid element. So I have to have some sort of body forces acting to actually change momentum, like gravity. And gravity will be the most common force. This sounds relatively simple. What will be complicated is that shell and accounting for all of the type of momentum that I need to balance. Okay, so let's do an example. And we will always need boundary conditions, and we will mention them as we go. The most common one is that if I have a fluid in contact with the surface, the velocity at the surface and the fluid have to match. At the boundary of two fluids, I will also match velocities within one fluid versus the other fluid, even though two different fluids will have two different viscosities. In other words, two different types of resistances to movement, right? So in themselves, they might have different velocities within. All right. This is just a long way to do the same. This is more for your notes. All right. So let's do one of these shell momentum balances. And this example will be, it's from your textbook. So example, oh, I'm still in yellow. And this is chapter 2.1 in BSL. So we will have steady state laminar flow of Newtonian fluid. Fluid with constant density. Quite a bit packed in here in terms of assumptions. Steady state means I don't change in time. Okay? So steady state, no change in time. Okay? Laminar flow is the flow regime. In this course, for the most part, we are going to be dealing with laminar flow. For turbulence, we will actually add correction factors. So this is orderly. It's laminar, so I have sort of layers of fluid. Newtonian, that's great because my rheology is pretty simple. What is Newtonian fluid described with? I have only mu, right? And that mu doesn't depend on shear rate. Awesome. And then constant density, I don't change my density, also makes my life much simpler. It's also incompressible, so under large pressures, I'm not going to change my density, for instance. And that's great. That's often so called also incompressibility. Simplifies things. I have density rho. So this is rho density. Or rather, this is how I write rho, which can confuse people. So this is basically, I described the fluid and its flow regime. The second step is, well, what is that fluid doing? Where is it flowing? And this fluid is flowing. Fluid. So this is first, second fluid is flowing down a gentle slope. Gentle slope. I'm going to draw that slope. And I'm not going to draw it very gentle because if I draw it too gentle, it's going to look horizontal. I don't want that. So I'm going to exaggerate that a little bit. Okay? But in reality, it's much more gentle than what I'm drawing. Okay? And now that I'm at it, the slope is beta. And the slope is three-dimensional, but I'm going to assume that's going to be assumption number one, that nothing really changes in that other direction going in. So now I have a thin fluid, so I'm first assumption is nothing changes. Now what was this? I don't know. Into the paper or into the screen. I'm writing on a screen. Okay. So I'm just gonna kill that. I essentially have a 2D problem, right? 2D projection will be enough. Okay. And yes, I'm gonna actually then now erase my drawing to simplify it. Okay. Okay. Great. I have a thin film, and I'm again gonna exaggerate it. So second thing, I have a thin film of fluid, and I'm gonna draw it in a slightly. Oh, what happened here? Okay. Film will be blue. It's water. Oops. And my film is going above the. And this is unfortunate, but book uses delta for the film thickness. Where did it go? Okay. Delta. Delta is film thickness. Not to be confused with the identity matrix. Okay. And this overall, I have length L. My third assumption is that I'm in a very nice laminar flow. Everywhere now, if I was actually ensuring that there's a film flowing down a plate, I would have to release it from some reservoir. As I'm releasing it, there's a geometry change. There are ripples, right? And then as I'm falling off this part, there might be ripple effects too. I'm assuming that I'm away from that. I'm somewhere in the middle where I don't have, those are called entry-exit effects. So that's my, another assumption is no entry exit effects. I have nice laminar flow everywhere. Excellent. So now we choose a coordinate system. I need two coordinates. The third one into the plane. Whatever I call it, I will ignore it. And I don't have the dependence on it. We're going to choose the one, and this is now a matter of choice. But I'm going to also assume that my thin film does not change thickness. If you're an experimentalist making sure that that happens in the lab, it's called good luck, but we're just going to assume that that's the case. Okay. So I'm going to place my coordinate system, and I'm going to redraw this slightly. Oh, come on. Where did it go? I'm gonna place this. Wow, Masha. I want to change the color. Okay, so this is my film thickness. So I'm gonna place this coordinate system right here. And this is going to be my Z, and this is going to be my X. So I'm aligning it with the slope. That simplifies my life. I'm aligned. If I'm not aligned, I'm going to have full tensors over there, so I want to avoid that. And I'm going to assume the following. This film is not changing thickness, and I'm in the laminar regime. Okay? So my velocities are kind of like orderly, and their vectors, they're parallel to the slope. Yes? I don't have anything really, because the slope is so gentle, I don't have anything falling down orthogonal to them. Yes? It's a pretty big assumption, but for thin film it's fine. Okay. So fourth assumption, okay, laminar orderly flow with velocities parallel to the slope. With velocities parallel. I really don't know what change. I press parallel to the slope. I have pretty big fingers, so I keep pressing this little button that then extends the line. So I don't have, the only velocity that I really have is Vz, yes, is non-zero. And that Vz will depend on x, where I'm moving through the different layers of the fluid. Vz of x. My Vz does not depend on z, but I also assume that I'm not accelerating down the slope. So I'm ignoring it. So I am ignoring acceleration in z and Vz of xz dependence, right? So I'm just ignoring that. Because if this was a bigger slope, I would expect acceleration, right? So each layer has different velocity. And I'm assuming that Vx is 0. Right? So I don't have the component going down into the slope. Orthogonal to the slope. Only parallel to the slope. Very orderly world. Is this world real? Not really, but it's a pretty good assumption for relatively thin film. That's why I'm calling it a film. Okay, it doesn't have a lot of thickness. So what is the momentum that my particles, for the most part, my fluid components are having? So I have z velocity that is non-zero, so majority of my momentum is z momentum. X momentum doesn't exist. X momentum is 0. I can go and calculate it, but it's 0. It's the momentum transfer in x. Of the x momentum transfer is not going to be there. And that's what simplifies my life. And that's what you're looking for in these things. And so you're looking at yourself to align yourself with the geometry, simplify your life. as much as possible. And that's an approximation, but we always work with approximations. Okay. So basically, I really have Z momentum transfer. Transfer is what we are looking for. That's going to then tell me setting up balance of Z momentum transfer will ultimately give me these velocities. Okay, so I'm going to calculate velocity distribution. Now this Z momentum, nevertheless, I'm in a two-dimensional world here. So the Z momentum can transfer across both X planes and Z planes. And my next thing is I'm going to draw it really small here. We're going to expand it really next time. So I'm going to get myself a little shell here in the fluid, right here. That is my shell. And then I'm going to blow it out. The shell is rectangular. It has four sides. And the way we will balance momentum is we're going to go to all sides and see what's coming in and what's coming out. Yes? And that's going to be our momentum balance. Our next task blow up the shell, right? And balance Z momentum coming in out of that shell. Which momentum? What are the components? What parts of it I'm going to have? This one, and it's full glory. So all of it. Okay. So C. Okay? All right. So we're going to balance that next time. And this, since I'm in 2D world, the components of momentum are Pxx, those are all of them. We're going to focus on the Z momentum components transferring. Yes? Okay. Okay.
I was thinking, I was like, wait, where's the chicken? He was like, oh, I forget the line. We do, but like, when we went to we all chicken, we went to HEB and all chicken. I made this like on Tuesday, because everybody is really bad at cooking, because the guy who's up, he's really bad at cooking. They all